Hello everyone, my name is Lulin Zhang. I am a PhD student under the supervision of Ewelina Rupnik and Marc Pierrot-Deseilligny. Today I'm going to present our work, Feature Matching for Multi-Epoch Historical Aerial Images. Our method is not only suitable for historical aerial images, but also for satellite and modern images, as well as mixed images. This is practical for georeferencing historical aerial images because satellite and modern images are often accompanied with georeference. Historical aerial images are images taken with analog cameras, then digitized by scanning the old negatives. They have the following merits. Firstly, high spatial resolution, which allows generating precise DSMs. Secondly, short time interval, which allows high frequency change detection. Thirdly, stereoscopic acquisitions, which allows 3D mapping. These merits make historical aerial images valuable resources for environmental monitoring. Assuming we want to do change detection and we have images taken before and after the change. In order to do multi-epoch comparison, a bundle adjustment is required to estimate the image calibrations. To do bundle adjustment, we need to find the matches, which means similar points, between the images as observations. Finding matches is a crucial part throughout the procedure because even small inaccuracies in the location of matches can result in large errors in multi-epoch comparison. It is also the most delicate and difficult part because for images taken at different epochs, we can see not only the scene changed, but also we have different image tones, scopes, resolutions, and so on. With no surprise, state-of-the-art failed to find good matches. Therefore, previous work often involves a lot of manual job, which is very laborious. Our goal is to find a lot of good matches automatically, like this. If we compare the problem to a puzzle, here are the pieces we have. Firstly, we have state-of-the-art feature matching methods. There are a lot of other methods, but superglue and SIFT have the best performance according to the image matching challenge. Superglue is deep learning method and SIFT is traditional. We want them to be time invariant, rotation invariant, and suit large images. Unfortunately, neither of them meets all the conditions. As materials for matching, we have RGB images and DSMs. DSM stands for Digital Surface Model. It can be easily generated within each epoch with the SIFT or superglue. Here, I displayed the RGB images from different epochs in the left column and the corresponding DSMs in the right column. As can be seen, the appearances of RGB images changed a lot, while the DSMs stayed stable over time. However, DSM has its own shortcomings. For example, it doesn't have rich textures and it contains noises that are not tolerable for recovering accurate matches. In other words, we cannot solve the puzzles with these pieces. Therefore, we came out of 3 ideas and used them in our workflow. The first idea, rough to precise, is our key idea. We firstly perform rough matching with DSM. It will give us an initial result which is robust because DSM is stable over time. Then we perform a precise matching to improve accuracy, leading to final results. This leads to our first contribution. It brings time invariance to any features. For example, even though SIFT is not time invariant, when combined with our rough to precise idea, it could produce reliable results, thanks to the help of DSM. The other two ideas, tiling scheme and the rotation hypothesis, are adopted in the middle of both rough and precise matching. The former leads to our second contribution, which is to scale up deep learning methods like superglue, and the latter leads to the third contribution, which is to bring rotation invariance. Here, I displayed a pair of multi-epoch images. The overlapping zone is indicated as red rectangles. If we apply superglue directly on it, we get very few matches. But if we combine it with our rough to precise tiling scheme and rotation hypothesis ideas, we can see the matching performance is improved significantly. Here is the comparison of SIFT with and without our rough to precise. As can be seen, SIFT found 0 matches, but after combined with the rough to precise, we found a lot of matches. Let's show an example of our results. The test site is located in Kobe, Japan. There was an earthquake happened there, and we have images taken before and after the earthquake. In the left, we show a pair of multi-epoch images. The overlapping zone is displayed with the red rectangles, and we show the matches of SIFT, superglue, and ours. As can be seen, SIFT and superglue failed to find any good matches, but ours found a lot. Based on the matches we found, we compare multi-epoch to calculate the ground displacement. Here we displayed the ground truth in the left and ours in the right. Ground truth is provided with a lot of manual work, which is laborious, but ours is completely automatic. According to the ground truth, there is a fault here caused by the earthquake, and the displacement is indicated as small arrows. On the left side of the fault, the arrows are upward, and on the right side of the fault, they are downward. In ours, the fault is indicated as a dashed line here, and the ground displacement is indicated as colors. Blue means upward and red means downward. As can be seen, our method recovered the same signal as ground truth, which is upward on the left side and downward on the right side. Here I displayed more information related to our method. First of all, collaborations and applications. Currently, we are collaborating with IPGP and KIGAM for displacement caused by earthquake. Another one is with CNREP for displacement caused by landslide, and also with the University of Pavia for Badland evolution. Beyond these collaborations, we also tested our method on urban expansion, glacier, and land use evolution. Here I displayed the test site of our experiments in each application. Most of the results can be found in our publications listed here. You can find more details about our method, codes, tutorials in the QR codes on the right side. That is all. Thank you for your attention.